Hi, in this video, I want to take a look at this circuit that I've drawn on the screen here. Now, this is called as the common emitter configuration. And one of the reasons why this is called the common emitter configuration is because the emitter here is connected to the ground. So it is basically uh, the common point of your circuit. It is the point from where all the other voltages are measured. So the collector voltage is basically measured with respect to ground, but the ground is connected to the emitter. So this is called right. And similarly, the base voltage is also measured with respect to the emitter, and therefore we call this the common emitter because the ground is connected to the emitter. Okay. And what I want to do as I look at this configuration is I want to look at the effect of VBE on the functioning of this transistor. So I want to start with a very low VBE, let's say 0 volts, and then go higher and higher and see how this VCE changes, okay, as a function of VBE. So what I'm saying is that I want to plot a graph like this. So on the x-axis, I want VBE, and on the y-axis, I want to plot VCE. Okay, let me just change this small v to a capital V. Usually, we use a capital V to denote DC signals, and that's what I want to do here. Okay, so I want to start with VBE equal to 0 and then keep moving higher and higher on this axis and see how VCE changes. Okay, so let's say VBE is equal to 0. So when VBE equal to 0, the emitter is already connected to 0 volts. So how is the emitter base junction going to be? What is the is it going to be reverse biased or is it going to be forward biased? So you can see that it is going to be reverse biased, right? Because this is 0, this is 0. There's no voltage here to switch on that particular junction. So this is going to be reverse biased. Similarly, what about the collector base junction? It's also going to be reverse biased, right? This is connected to VCC, which VCC is basically the positive power supply, so probably 10 volts or 15 volts, while this is 0. So it looks like the collector is going to be more positive than the base, and therefore this is also reverse biased. So the transistor then is in cutoff mode. And you could have got this more straightforwardly from just the assumptions of the cutoff mode. Remember, the cutoff mode, the transistor is in cutoff mode when VBE is less than 0.7 volts, and that's what here it is, right? So in the cutoff mode, we already said that the base current is going to be 0, and the emitter current is going to be 0, and the collector current is going to be 0. So there is no current flowing in the transistor. So if there is no current flowing, if IC is equal to 0, what is VCE equal to? So VCE is this voltage VCC minus the drop across this resistor. But if there is no current through this resistor, the drop is 0. So VCE is equal to VCC. Okay, so let's draw that. So what we get is when the transistor is in cutoff, you get VCE is equal to VCC, and that happens till we reach cutoff, right? And let's say till the transistor is in cutoff, and let's say the transistor is in cutoff till this point. And what would this point be? This point would be something around, let's say, VBE equal to, let's say, 0.5 or so. Okay. Okay, let's look at the functioning of the circuit in the active mode. Now, what happens in the active mode? In the active mode, IC, this current is beta times IB, right? And beta is a large number, let's say 50 or 100 or something like that. But what is IB in this case? Now, we don't know IB here, but we can calculate it, right? Because you remember we had calculated, we had an equation in the case of diodes between the diode current and the voltage, and that was given by, so let me write IB is going to be some current Is e to the power VBE over VT, right? Now, if that is IB, then we can calculate what is IC. So let me just write the equations here, right? So IC will be equal to beta times IS e to the power VBE over VT. Now, having IC, we can calculate VCE, which is going to be VCC minus ICRC, which is equal to VCC minus beta ISRC e to the power VBE over VT, right? And now you can get VCC from this equation here. Sorry, VCE, the collector emitter voltage in the active mode from this voltage. So you can see that what happens is as VCC, as VBE increases, this this term becomes larger and larger in value, and therefore VCE becomes smaller and smaller. Okay, and at some point VCE will become so small that it becomes less than VBE, and then this junction becomes forward biased and we enter into saturation. Okay, so the voltage then in the active mode will look something like this, right? It goes down and it's non-linear, and it goes down till VCE is uh, VCE is the relationship between VBE and VCE becomes very less. So VBE becomes equal to 0.5 plus VCE. Okay, and now you could think about the saturation mode. The saturation mode, in the saturation mode, VCE is just equal to 0.2 volts, right? And therefore you can just draw this as straight here. And that's what you would expect, because the difference between VBE and VCE is 0.5 volts, which we said was the edge of the active mode. And after that, VCE becomes 0.2, which is the same as the base collector junction voltage being equal to 0.5 volts. So let's just draw this and mark this point as, let's say, 0.2 volts. Okay, so what we have is, this is our cutoff region, right? This region is our cutoff, and in the cutoff your VCE remains equal to VCC, and then you have the active region in which the voltage actually reduces kind of in a non-linear fashion, and then you have the saturation region where VCE becomes constant again and is equal to 0.2. So it's very, very small. So you can see that in this case, as VBE increases, VCC reduces. Of course, the reduction mainly happens in the active mode. In the cutoff and in the saturation mode, VCE remains more or less constant. In the next video, we'll take a look how this helps us to think through the functioning of a transistor as a switch and as an amplifier.